Okay, hey guys, I wanted to elaborate a little bit on something that I said in the last video about where to find your maximum moment, and I think it would be best if I explain what I was talking about with an example. So, and I have to use a pen here because my handwriting gets very bad when I have a marker. Let's say I have some distributed load like we have in the problem of W on some length L on 3. The maximum, like you should find in your homework solution, is here, and that has a height of 2L on 9. This is theta 2 theta on 3. This is theta on 3. I could put the load right here, right? So in case A, I'm putting the load right at the... I'm putting the load right here. If I do that, I'm going to find that I get a trapezoid section, right? This is 2L on 9. This height by similar triangles will be L on 9. The total load will be 2L on 9 plus L on 9 equals 3L on 9. That is the height. I need to divide this by 2, divide this 2. This is the average of the heights. And if I multiply this by the base, I'm going to get that this is going to be 1 on 3, L on 6. This is going to be L squared on 18. So the area of this trapezoid will be 18, L squared on 18. But I could, do you guys agree that this value is larger than this value? So if I shift my load over just a little bit to the left, I'll actually increase my load. And I'll keep increasing until I reach some ratio. And basically what I'm looking for is I want the heights of these 2 points to be the same. So if I look at this more closely, the idea is that because this slope is steeper than this slope, I'm going to have most of my load on the right side. But I still need to take advantage of the fact that these values are very high. So how do I get my maximum? I use my ratio of the bases again. Basically, I'm going to want 1/3 of my load. This is L on 3, right? I'm going to want 1/3 of my load to be on this side. I'm going to want 2/3 of my load to be on this side. If I do that, I can use similar triangles again. I'll find that the height of this little rectangle here is 4L on 27. The height of this triangle is 2L on 27. The width of the triangle, so the area of the triangle is 2L on 27 times 1/2 times L on 3. The area of the rectangle is 4L on 27 times L on 3. This is going to give me... I can barely see what's on the screen here. This is 5L squared on 81. This is actually larger than the value we got before. 5L squared on 81 is greater than L squared on 18. If we actually calculate this, we end up getting that 5 on 81 is 0.06173. 1 divided by 18 is 0.055. So we get that 0.06173 is greater than 0.0556. So basically you want to move this load around until you get the same height across the top. Now this is only for distributed loads. Point loads are a different story. Point loads, you do not have to worry about this little mess here. All you have to do I don't want to say all you have to do. The professor has been going over this in class, but basically you want to do is, let's say you have 2 point loads. Moving across the bridge, you can find the centroid. That'll give you some net section, right? Where, so this will be 2p, and this will be L on 2, where this is some length L. What was I gonna say for this? Right, you can move this around on your diagram, but usually what will happen is that because one of the wheel loads is, usually the wheel loads aren't exactly the same size. Usually the loads you're concerned about are like 2p, 2p here. So this would be something more like 3p, and this would be at 2L on 3, and this would be at L on 3. So normally you would have some 2p, load 2p here, and you'd normally just want to put the heaviest load at the vertex. You'd want to put the heaviest load here. But you do not have point loads for this problem, so you don't have to worry about that. You can worry about that for the exam. But yeah, let us know if you have any other questions.